Hi there, my name is John and I'm the team lead of Cornell Mars Rover, and we're proud to unveil this year's rover, Athena. Cornell Mars Rover is an interdisciplinary project team composed of 46 undergraduate members who are split into 6 different sub-teams. The task sub-team, which develops the rover's robotic arm and drill, the drive sub-team, which develops the rover's suspension, wheels, and electronics housing, the electrical sub-team, which oversees the rover's communication, electronics design, and embedded firmware, the software sub-team, which oversees autonomous systems and controls, the science sub-team, which oversees Martian and MDRS research, as well as onboard sensor selection for the science task, and finally the business team, which oversees team finances, web and presentation design, sponsorships, and outreach.
Throughout the design process, the team is careful to design a rover that remains under both the mass and monetary budgets for the URC. The academic year is split into 3 development timelines: a design phase from August to November, a manufacturing phase from November to January, and a testing phase from February to May. We've made significant improvements to the rover design this year to meet the new challenges of the URC. We increased the strength of our suspension to increase durability and designed a modular dampening system for each task. The electronics core has been manufactured by Protocase and features external-facing power pole connections to simplify wire routing. The frame has been redesigned to be roughly twice as strong, but only 5% more massive than previous designs. The rover uses wheelie pneumatic tires to increase the dampening and deformation of the wheels. These wheels are designed to navigate across the desert and deform over terrain such as the rock garden.
This year, we have designed a semi-modular arm in order to meet the varied demands of the URC. In the equipment servicing configuration, the end effector uses belts to unscrew the regulator and non-back-drivable rail-guided fingers to increase human operator precision. The wrist consists of a bevel gear differential to give us 2 degrees of freedom. In the extreme retrieval and delivery configuration, the end effector and wrist feature much simpler and more robust designs, while a mount on top of the rover provides a stable stowing position for the arm during rough driving. The drill has been outfitted with a linear actuator to make drilling beyond 5 centimeters for a soil sample in the science cache task more efficient and reliable. The sample container has 3 separate partitions with removable boxes for different samples, allowing convenient and sterile sample transfer to the lab.
The rover uses GPS, inertial measurements, LiDAR, and computer vision in order to complete the autonomous task. We navigate towards the target gate using provided GPS coordinates, while LiDAR is used to avoid obstacles. Once near the gate, an image mask is used to differentiate the tennis ball from the Martian desert and determine the rover's distance from the tennis ball. Once in range, the rover will stop. We have developed a new framework on top of Robot Operating System, or ROS, that provides local machine configuration and dependency management. This lets us design flexible and resilient software. 2 12 dBi omnidirectional antennas on the rover allow it to communicate wirelessly using 2.4 GHz ubiquity transceivers with a 16 dBi sector antenna at the base station. This has proven to allow operation beyond 1 kilometer, even with partially obstructed line of sight, and provides sufficient throughput for several video streams. The rover is also equipped with a 22 amp-hour lithium polymer battery, which in tests has sustained continuous rover operation for over 3 hours on 1 charge. Firmware on our PIC32 microcontrollers enabled the smooth control of all of our motors.
In order to determine the habitability of a site, we will be adhering to the science theme of the Mars exploration missions, which was Follow the Water. The onboard analysis for this rover includes tests for soil moisture content, soil temperature, air humidity, and mineral fluorescence. The goals of the first 3 tests are to determine if water is present at the site, and if the environment is conducive to most forms of life. The fluorescence test utilizes long and short wave ultraviolet light and fluorescent properties of minerals to study the mineralogy of a sample collected. Our rover will also carry cameras, which will be used to identify fluvial features, which provide evidence of past water flow, and to record a stratigraphic profile. Our lab tests include a series of chemical tests to look for common organic compounds, as well as a polarization test that utilizes the polarizing properties of crystals to identify minerals.
From now until competition, the team will focus on testing the rover. Each member is assigned to a testing team that prepares the rover for an individual URC task. The team will additionally partake in 2 mock competitions. At mock competitions, we travel off campus to simulate the entirety of URC in 1 day. These allow the competition team to practice under time-constrained conditions to fully prepare to excel in the University Rover Challenge.
Athena is just about ready for URC, and so is Cornell Mars Rover. We hope to see you in Utah.